Hello, guess what day it is today? It's my birthday. And guess how old I am today? The song is kind of a hint. Also, my age is a perfect square. Anyway, so still going to take a while for that to come. All right, today what we're going to do is talk about masses on a spring. There it is. All right. So, yeah. Well, welcome today to another little mini lecture. We're starting set 13 on second order modeling. And what is the key of the most important second order modeling in the history of science? Newton's laws of motion, in particular, force equals mass times acceleration, F equals ma. And you know, Newton had his great aha moment about universal gravitation while he was at home because Cambridge University was closed down. I mean, they had a terrible bubonic plague in around 1665 to 1667. The university was closed for a few years. A quarter of the population of London died in that outbreak of the bubonic plague. So talk about social distancing wow, that must have been intense back then. But anyway, yeah, let me talk a little bit about Newton's realization with the apple. The apple probably didn't fall on his head, but he probably did see an apple falling. And that's, you know, gravity. We've lived with gravity. We understand gravity. And I like to think, I have no reason to believe this, I like to think he was sitting there near the tree looking at the moon, that sometimes you can see the moon in the middle of the day during the right phase. And his amazing realization is that the same force of gravity that pulls the apple down here on Earth keeps the moon in its orbit. And he had done the calculation. He was able to do the calculation and figure out, given that assumption, what the period of the moon will be. He rushed, I'm sure, to do his calculation, and he came up with 28, 29 days, something like that. And it must have been the greatest aha moment ever. All right, so let's talk a little bit more mundane about masses on springs. I have this slinky here, makes a nice noise. Okay, and I've got a yardstick. We're going to be using lots of units. This yardstick is in inches, it's not meters. I put little mark every 10 inches. I've got three masses. I've got the large keys. I've got the hand sanitizer. You might have seen me, I clip it to my belt. And I've got the small keys. All right, so I've weighed all of these things, or I've massed all of these things. Here, the large keys weigh 45.2 grams. The hand sanitizer, 31.9 grams. Small keys, 37.7 grams. Okay, so we have Hooke's law for this spring. We're going to see if Hooke's law works, and we're going to use that to estimate the predict the frequency of oscillation when I put some of these keys on this spring here. So to figure out what the K is for Hooke's law, force equals K times X displacement. The force is proportional to displacement. All right, we'll start by measuring how far the bottom of this little hook is. Okay, down. So the hook is at about 2.2 inches. Okay, now one estimate of the spring constant would be I take the keys. I told you how much, what their mass is. I can convert that to a weight and see how far that stretches. Okay, in fact, that's the way that a lot of your some of your Weber problems are going to be. We're assuming that Hooke's law holds all the way from before. So now it gets to stop it, it gets to about 13.8 inches. All right. So with the big keys, it's 13.8 inches. What was it unladen? I don't remember that. Does anybody remember that? I guess I'll have to do it again. I think it was 2.2 inches, yeah. We'll assume that was 2.2 inches. If not, you can hurt it. So 2.2 inches. All right, so now, so that distance and that weight can give you an estimate for K. I don't think that's going to be a very good K. I'm going to estimate K from everywhere between having just the big keys and the big keys plus the hand sanitizer plus the little keys. So let's add this hand sanitizer and see how far it stretches. And then, all right. Here we are at about 20, let's say 20.8 inches. All right, so here I have the 2.2 inches unladed, 13.8 with just the big keys, 20.8 with the big keys and the hand sanitizer. And this is actually, I'm going to be estimating that frequency of oscillation, or that period, in a minute, okay? So now what we're going to do is add the little keys and see how much farther it stretches. Okay. All right. I'm going to call that 30.0 inches. 30.0 inches. Now I can take these 4 data points and graph them and see if they fall in a line. Of course they won't. Are they approximately on a line? I don't know. But I bet these 3 do pretty well. I'm not sure. We'll figure it out later. I'll come back tomorrow and get my calculation. I hope you can do it over the next day. All right. So what I want to do now is take off this, okay? So I'll get a good estimate for K here by taking the displacement with a little less mass, a little more mass divided by the distance. That would be a good K, the K that's good for right now, right? All right. So using that K and that M, the mass, we'll be able to compute the frequency of the oscillations, okay? The frequency in radians per second is, we often call that omega naught, omega sub 0, is the square root of K over M. And you can use that to find the period. 2 pi over omega naught will be the period. So compute the period and then we'll do a measurement and see if you're right. Why don't you pause it, compute the period. All right, welcome back after you paused it. So I'm going to take this, I'll just, don't have to, okay. I started this going. So now I think the easiest thing to do is think about the period from the top. When it gets to the top, kind of start a timer when it gets to the top. And actually you can do that by pausing the YouTube video and it tells you what the time is, okay? So figure out how long it takes to do 10 oscillations, divide by 10, which is a piece of cake, of course, and we can find the period of one oscillation and see how close you were, okay? And while we're at it, there's one more thing I want you to do is get a rough estimate for the damping constant, okay? We'll talk about the non-dimensional damping constant later, but how many oscillations did it take for the amplitude to decrease to a half of the original amplitude, okay? You might be able to do that using the little dots. I'm not sure if you can see that, but that's kind of secondary. The main thing I want us to do is use all these measurements to compute a meganaught, compute the period, estimate the period, and then compare it with the observation. Okay, clock is on the wall, says it's time to go. So, all right, we'll see you tomorrow on the next installment. Stay well and have fun. Okay, bye.